Hi there, welcome to the explainer video for ConceptGraphs. ConceptGraphs builds open vocabulary 3D scene graphs that can be queried with natural language. Given an input sequence of RGB plus depth images with poses, ConceptGraphs uses open vocabulary instance segmentation models to detect 2D segments in those images, grouping them over time into potential 3D objects. Using large vision and language models, we extract image features and captions, which are then used to build an open vocabulary 3D scene graph. Here we can see ConceptGraphs in action. The built scene graph can be used for many downstream tasks. First, let's demonstrate localization via a particle filter. Here, we can observe the distribution over the possible locations within the map converge to the correct one. With reference to a built map, we can also detect new objects that are added or moved in the scene, shown in green here. Moving on to a real-world setting, here is a room at the University of Montreal being scanned with an RGB plus depth camera. To the left, we can observe the scene graph being built incrementally by ConceptGraphs. Once built, the scene graph can then be queried. Here is a visualization of the built scene graph. Time for a query. How about something to wear to a space-themed party? First, let's try to resolve the query via clip similarity. This is simply fetching the object whose clip feature vector has the highest cosine similarity with the query's clip feature vector. Here's a heat map style visualization where the high clip similarity objects are highlighted in yellow and low clip similarity objects are highlighted in blue. Here, we can see that a t-shirt with the NASA logo was selected. That's pretty good. Another way to resolve the query is via a large language model, or LLM for short. We feed the LLM a serialized scene graph in a simple JSON format. The LLM can then use the object captions to select the most appropriate object for the query, shown here in pink. Looks like we get the NASA shirt again, same as clip this time. Both methods work well for this query. Let's try a different query. How about something to secure a broken zipper? Let's first resolve the query via clip similarity again. Here, we can see that the top selection is a backpack. This is not very surprising. The zippers on the backpack cause it to have a high similarity with the queried text. Let's see if the LLM approach can do better. As we can see, the LLM selects a roll of yellow tape, which is a much more appropriate response for this query. While clip similarity works well for straightforward descriptive queries like red shoes, it struggles with queries involving negations, for example, shoes that aren't red, or complex queries involving affordances, like the broken zipper query. The LLM approach, however, doesn't have these problems, and performs well even with highly complex queries. Now, we can demonstrate some real robot experiments that use this approach. We use a Clearpath Jackal robot for our navigation experiments. Here, we can ask the Jackal to find some footwear for a Ronald McDonald outfit, and see that it finds the red shoes. We also have queries where the object has been moved, so the Jackal will no longer find it at the original location. In this scenario, ConceptGraphs can suggest a likely location where the object may have been moved. In this case, it's a nearby shoe rack. We also handle visual queries. Here, the input query is a picture of Michael Jordan and the text, "something this guy would play with." ConceptGraphs can infer that the user is looking for a basketball. We also perform a manipulation task where a Boston Dynamics spot robot picks up and moves the queried object. The query here is Cuddly Quacker, referring to the duck plush toy. The grasp point being used can be seen at the bottom left. Here, we have another manipulation example where the query is something healthy, which is used to find the fruit present in the scene. Almost there. Nice. Last but not least, we also perform a traversability task, where a trapped Jackal has to navigate to a goal location and use the scene graph to determine which of the obstacles can be pushed through. This feature can be used to navigate in a cluttered environment where an obstacle-free path cannot be found. To better understand how ConceptGraphs enables robots to perform such tasks, let's take a closer look at our method. ConceptGraphs takes as input a set of RGB plus depth images with poses. We use open vocabulary object detection and instance segmentation models to obtain 2D masks for the objects in those images. Using the depth information, we can now project these segments into 3D to get individual point clouds for each object. Using the images again, we can now crop our image around each detected object and feed those crops to a vision language model such as CLIP to extract semantic feature vectors. Once we have each object's point cloud and semantic features, we can now measure their spatial and semantic similarity to existing objects in the map, and each object is either merged into one or added anew. Repeating this process for each frame allows us to incrementally build an object-based 3D map from our input images. Once the map is built, we have all the nodes for our scene graph, and now we need to construct the edges. Using simple heuristics to guess which object pairs may be related, we can query a large language model to determine what kind of edge, if any, is appropriate, such as a cup being on top of a table. This finally results in the full 3D scene graph, which contains rich semantic features for each object and also encodes the relationships between them. For more details on our method, please check out our paper. All of the code for ConceptGraphs is open source. We've made significant updates to the codebase since the original release in September last year and expect to continue doing so. What used to be separate scripts each for running the detections, 3D reconstruction, and scene graph generation have all been refactored and consolidated into one mapping script, which includes edge construction, meaning the entire scene graph can be built incrementally in a single loop. We also know that being able to quickly visualize and inspect things is crucial for working with 3D data, especially a mapping system, which is why we've integrated visualization directly into the scene graph construction process using the Rerun SDK. This allows you to inspect and interact with the map as it's being built in real time. You can toggle the visibility of any map component, such as an object's point cloud or bounding box or an edge, and we provide various class labels at different levels of detail. You can also, of course, move the camera around and scroll through the timeline. To inspect an object more closely, you can open it in a separate viewer in isolation from the rest of the map. We also log the input images to the viewer so you can always see the current input frame and its detections that inform the 3D map construction at that time step. All of these features make it much easier to understand how the algorithm works and tune its hyperparameters to your specific use case. And speaking of your specific use case, we've also added support for using iPhones with LiDAR as an input sensor, making it easier to get started with building scene graphs of the real environments around you. Okay, wrapping things up, ConceptGraphs is a powerful mapping system that makes 3D scene graphs that can act as semantic world representations for robots, enabling them to interact with their environment in new and useful ways. It's easy to get started with, has good visualization tooling, and is only going to get better as it's under active development. You can check out our code at our GitHub repo and learn more about our method at our project page. Thank you so much for watching and have a wonderful day.